Hello, I'm Sandeep Avaru from the Department of Electrical and Computer Engineering. The existing treatments for neuropsychiatric disorders are not even 50% effective. And this is partly due to the fact that diagnosis and treatment is very much based on the symptomology and not on the underlying mechanisms. Dysfunctional cognitive control is a common theme in a wide variety of these mental disorders, such as OCD, addiction, depression, schizophrenia, and even autism. Although we don't understand how these dysfunctions are encoded in the brain, what we know is that electrical brain stimulation can enhance cognitive control and help the patients make better decisions as long as we target the right brain regions. But there is no well-defined neural signature for cognitive control, so it's really hard to find these right brain regions. And a part of this work is to try and answer the question as to when would be the right time to intervene and provide stimulus, and also what would be the best brain region that acts as the most optimal target site. To do that, we try to differentiate cognitive effort from background activity by using a task called the multi-source interference task. So this boils down to a classification problem between task and non-task. And the second goal is to look at the brain regions, brain networks, and try to identify the hubs, the key brain regions that are involved in task engagement. One of the good things about cognitive control is that it can be readily measured by using a task. A typical trial in an MSIT looks something like this, where a fixation cross is first presented for 2 seconds, followed by 3 numbers. One of these 3 numbers would be the target, and the other 2 are called distractors. In this case, the target is a 1, and therefore the correct response would be to press the first key on the keypad. In the second example, the target is a 2, so the right response would be to press the second key regardless of the position of the target. And as 10 participants performed this task, we recorded their brain signals using depth electrodes. And that's one of the interesting things about this data set, is that we have highly invasive data from human beings, which is not really easy to acquire. And this was possible because these patients were all epilepsy patients who volunteered to perform the task. This is the classification pipeline where we start with the data set, construct the networks, extract features, and use those features to classify and say whether a recording has been recorded during the task performance or during background activity. One of my main contributions in this process is this little box called MVNM, which stands for Maximal Variance Node Merging, where I take a channel level network where each node in the graph is a channel of recording and convert that to a more meaningful, more interpretable region level network where each node is a brain region. And I do that in such a way that the most optimal inter-region connections are extracted without losing a lot of information. This is an example of a correlation network that we estimated, and that's the reason why this is a symmetric matrix, and this is an example of a causal network that's estimated using this approach, and this is a non-symmetric, it's asymmetric matrix. Using this approach, we were able to attain an accuracy of 85.2%, which was a notable improvement over the 78% using an existing approach in the literature. And this answers the question as to when would be the right time to stimulate, because now we're able to say whether a cognitive effort has been exerted or not. And then we go back and look at the best features and find out that there are 3 brain regions that really stand out in terms of having more connectivity that is the dorsolateral prefrontal cortex, the temporal lobe, and the ventrolateral prefrontal cortex. So one of these brain regions could be a good site for stimulation. So this answers the question as to where would we stimulate. Thank you.